L.J. Steimle Enterprises thanks you for allowing us to introduce to you a new instrument designed specifically for the wavefront testing of optical quality filters, the Broadband Achromatic Twyman-green Interferometer, the BAT Interferometer. The collimated light arrives at the beam splitter. A portion is reflected to the reference arm, and the rest passes through the beam splitter into the test arm, then through the filter to the return mirror. The light from both arms recombines and interference takes place at the beam splitter. Let's look at a filter. The filter is held in this holder and inserted into the beam. Notice that the BAT can operate in a fully lighted room. This is not only more convenient, but reduces the risk of accidents. In the reference arm, we have a quartz window, which compensates approximately for the thickness of the filter under test. Not a required item, but it does enhance contrast in some cases. The wavelength is selected here and merely adjusted for the transmission region of the filter being tested. The digital readout of the monochromator gives the wavelength in nanometers. A small black and white CCD camera detects the interference pattern which is displayed on a 9-inch monitor. It is significant to note that the BAT is quite stable and requires no special surface table or vibration isolation system. A hard copy, an interferogram, is produced at the touch of a button by any one of 3 video copy processors offered. The 8x10 copy unit is shown here. The other 2 produce copies about 4x5 inches. The return mirror of the reference arm may be tilted by these 2 micrometers vertically and horizontally to adjust the fringe pattern as desired. The length of the test arm is monitored by a digital micrometer. The stationary background fringes you see there are due to reflections within the sandwiched type filter. Because of the very short coherence length of the light source, the 2 arms of the BAT must be identical in length within a few microns. Simply adjust for the highest contrast. Now let's remove the 2¼ inch square filter and test a 1-inch diameter filter from the beginning. Tune the monochromator to peak the intensity through the filter, and then we go into the alignment mode. Now you see here the beams from the two arms. We merely adjust one to superimpose it with the other. Let's turn the intensity down a little bit here and bring that up right there. Switch back out of the alignment mode, and now adjust the length of the arm until we see fringes appear. If this filter is thicker than the previous one, we move the arm in. If it's thinner, we move the test arm out. There we see some fringes coming in. Adjust the tilt of the reference arm a little bit. Peak up the fringe contrast, and there we are. The same shaft that rotates to select the alignment mode also slides in and out to achieve best focus. Focus does change slightly with large wavelength changes. The bat interferometer weighs about 45 pounds and is easily moved. This is the entrance aperture to the monochromator. Your light sources would be set up in this area. The Model 410 comes with a 150 watt quartz tungsten source, and the 210 includes in addition a 75 watt xenon arc source. This is the connector panel. Main power, video out, and two fused accessory outlets. Even turning this unit around has not disturbed the alignment of the system. As we see, the interference fringes still visible. For today's demonstration, we use this 150 watt quartz tungsten lamp with a 24-inch fiber optic bundle leading to the monochromator. There are two models of the bat interferometer: the 410, which covers the wavelength region from 400 to 1100 nanometers, and the 210, which covers from 250 nanometers to 1100 nanometers. Not all filter manufacturers will buy a bat interferometer to measure transmitted wavefront. But then, not all filter manufacturers want to produce a high-quality product suitable for the most advanced imaging systems. Let us build one for you to put you on the cutting edge of today's space frontier.